All right, so we talked about ice and uh, changes that were taking place in the Arctic and the Antarctic, and we looked at some evidence showing that of the ice and glaciers that are retreating and melting. So the question is, why is this happening? What's causing this? And many of you may already know, but what we're going to look at is heat, right? So more heat, the more ice can melt. Um, we've all experienced this, right? So there must be something that's adding heat to our Earth system for there to be some kind of melting of these glaciers and these ice sheets and the Arctic sea ice. There's clearly a temperature change that's been going on. One of the first things that we're going to look at is carbon dioxide levels, and we'll look at why we talk about carbon dioxide levels here shortly. But what we see in this graph, and this graph only goes back to 2006, but it's showing recently um, recent trends in carbon dioxide levels in the atmosphere. And you have this steady and continual increase of carbon dioxide in the atmosphere to where it's currently at is 409 parts per million. These studies started back in the 60s, I believe it was, in Hawaii with a scientist that started collecting this data, how much carbon dioxide was there. He was using the top of one of the volcanic mountains to take his measurements to try and get air that was as pure as possible. And that work has continued since then, since the 60s, and it has shown um, a increase, a rapid increase of carbon dioxide levels in the atmosphere. And once we saw that this was happening in the last 40, 50 years, we started to look at ways to figure out what CO2 levels were like in the past. This graph here goes back 400,000 years, and this is taken from ice cores. So as you would have learned in the last packet, ice cores trap air bubbles from the atmosphere of whenever that ice was laid down, get laid down in layers, and that air gets trapped. Well, we can thaw out parts of those ice cores and analyze the air that comes out of it, reading how much CO2 was in the atmosphere. And going back 400,000 years, you see this up and down trend of CO2. It goes up, goes down, it goes up, and it goes down. It never, at least in the last million years, because we also, instead of 400,000 years, in the ice core record, we can go back almost a million years. And we see the same trend, up, down, up, down, up, down, but never going above the 300 parts per million. We passed 300 parts per million in the early 1900s. 1950, we were just over 300 parts per million. And in the last 60 years, we've gone over 400 parts per million. So that change, that increase, is extremely rapid. It's fast enough to appear as an anomaly in the record. We haven't seen anything like this in the last million years or so. And if we look at an animation showing CO2 in parts per million and how it's gone up, if you while you watch this animation, the color change that you're going to see is just representing how high up that level got. So if it's over 400 parts per million, it's going to go into the red. And in the early 2000s, 2002, 2003, 2004, 5, it's in the high 300s. As you get into the later 2000s, you're going to get higher and higher, closer to the 400s and low 400s. So at this point, it's in 2008, and you can just start to see a little red tinge. And you'll notice a trend here. There's more of a band of dark red along the northern latitudes. So why would there be more carbon dioxide being released during the summer in these northern latitudes across Asia, Northern Asia, Europe, North America? There's this big release of CO2 during the summer. And you have to think about where CO2 comes from. Naturally occurring CO2 is going to come from trees. So that gets pumped out during summer, and then the planet evens it back down. There's some processes that pull CO2 out of the air. But during summer months, you get this big pulse of CO2. Now, as far as human CO2, we are constantly putting CO2 into the atmosphere. It doesn't change significantly from summer to winter, because in summer, we need electricity to cool ourselves down, and in winter, we need electricity to warm ourselves up. And when we talk about electricity, most of it is produced by burning fossil fuels. Okay? All right, so when we talk about the atmosphere and the layers of the atmosphere, that last animation I showed you was CO2 in parts per million, and it was taken from, it said the troposphere, mid-troposphere. Well, to give you a review of layers of the atmosphere, troposphere is all the way down here at the bottom. This is where we live. We live in the troposphere. Mount Everest reaches close to the top of the troposphere. The weather and clouds we see, the vast majority of them, are all within the troposphere. Our weather happens in the troposphere. And our jets travel just at that upper range of the troposphere as it goes into the stratosphere, which would be the next layer up. And then we've got the mesosphere, thermosphere, exosphere, which is right where the boundary of space is. I mean, you can see the thermosphere has the space shuttle and the aurora borealis. Mesosphere is where we see meteors or small rocks burn up in the Earth's atmosphere. But we're almost always concerned with the troposphere. That's the thickest part of our atmosphere because gravity's pulling down these gases close to Earth. It's where we're concerned about a buildup of CO2. It's where we're worried about heat getting trapped next to the Earth and warming the Earth. So it's important to understand that there's layers to the atmosphere, but the one that we're really concerned with is the one that we live in, the closest one, the troposphere.